Right, I think we'll get started. Hi everyone, welcome to today's COMET webinar. Our speaker is Dr. Stanley Yip from the University of Leeds. Stanley is currently a postdoc working on a NERC-funded magma project, which aims to benchmark numerical volcano deformation models to lab-based analog models. And today he'll be sharing some of his previous work, looking at how to integrate deformation and gas measurements and how these can provide insights into magma compressibility and magmatic systems. So the talk will be around 40 minutes, 30 to 40 minutes. So we'll have plenty of time for questions at the end. So if you have any during the talk, please put them into the Q&A at the bottom, and then we'll get to them during that bit of time at the end. Right, so that's all for me. So I'll hand over to Stanley. Go for it.
All right. Yeah, thank you, Anna. So this work itself is done during my PhD when I was still in Bristol, and that was and I've since moved on from Bristol to Leeds, and yep. So basically, I'll just be sharing what I've did for my PhD. Just drag this to the side. Okay. How do I hide the top bar? Never mind. So basically, yep. So there has always been volcanoes that's been erupting over time, and then over the years, there's like people seeing like volcanoes and like erupting, and then yep. But in recent years, there's more and more volcanoes that are being detected, and that's due to satellite measurements. So we could see that in like the early 2000s, there's a jump in the detections of erupting volcanoes, and that's due to the increase of satellites being launched. And here we've got observations that's being made in Sierra Negra 2005. Here we've got SO2 data that's by spectrometer. We've got thermal anomaly as well, and we've got deformation data from INSAR. So in this talk, and what I've done for my PhD project is I integrate observations of volcano deformation and degassing. And part of that is to try to answer like, why is there like the excess sulfur problem, and at the same time, why is there lack of deformation in some volcanoes despite erupting? So my project reconcile observations of sulfur dioxide degassing, deformation, and also extruded volume, and that is to normalize the eruption data. And the motivation over here is to understand like, how does the presence of gas affects deformation and degassing. So the presence of exsolved gas in magma itself would increase the compressibility of the magma. That would result in a muted deformation of its surface. And similarly, the presence of exsolved gas in the magma could lead to an increase in sulfur dioxide degassing that's being detected on the surface. So what I did was to use thermodynamic modeling of petrological data, and I compared that to global observations of volcano deformation and degassing. And the hypothesis over here is, as mentioned before this, is the presence of gas bubbles affects both observations. And I've got two papers out through my PhD project. I've got one that's still in preparation, so do look forward to that. So here's a simple conceptual model. Here we've got a deep reservoir with all the volatiles that's being that are dissolved in the silicate melt. And here we've got a shallower reservoir with exo volatiles. So yeah. So when we've got volatiles that are deep in the reservoir, they are all dissolved. And then so this is the volatile weight percent in the melt. And as the pressure decreases, these dissolved volatiles would exsolved into gas phase. And as they exsolve into gas phase, we see an increase in all of these volatiles, and that includes sulfur dioxide, which is readily observable by spectrometers. So normalized SO2 itself is sulfur dioxide gas normalized by the erupted volume. So here we see that per meters cube of magma being erupted, there's more sulfur that's being emitted. And with more volatiles being exsolved in the gas phase, there's more gas bubbles. This is in volume percent. And as these, as there's more bubbles or gas in the magma, these the magma density becomes less dense. And we use the magma density to calculate the compressibility of the magma. And it shows that when the magma becomes less dense, it becomes more compressible. And we use the compressibility of magma to calculate for the volume change. And we normalize that to the volume erupted to get the normalized volume change. And we see that there's less volume change as the magma reaches a shallow reservoir. And therefore, there's less deformation. And yep, here again, reiterating that I'm focusing on degassing and deformation itself. So before going into the details of like the sensitivity test, here I've got a sensitivity test of the crustal properties and chamber geometries itself, because these parameters are equally important in terms of knowing the deformation that's being seen and detected on the surface. So here we've got, we explored different crustal shear modulus. And then based on these values of crustal shear modulus, we calculate for the crustal compressibility. And we're not going to delve too much into this bit because it's not the main part of the talk. But the main takeaway over here is that crustal properties itself does play a huge role in terms of the in terms of deformation that could be detected on the surface. So if we increase the shear modulus, crustal shear modulus, by an order of magnitude, you could see that the normalized volume change increases, meaning there's less deformation that could be detected. And moving on to looking at volatiles and deformation. So here we've got a basaltic magma, and we could see that for a different weight percent of water that's in the magma, we see that an increase in water in the basalt increases the amount of normalized SO2, and the presence of water, the increase in the presence of water, means that there's an increase in the magma compressibility, and that means there's less volume change and deformation in general. And we compare basalt and rhyolites as well. And because rhyolites, which are more silicic and has more volatile content as compared to basalt, it produces more normalized SO2, and also it has more gases. So they have high magma compressibility and therefore, again, less deformation. Now we look into different eruption styles. In this case, I'll be explaining how do we look into the thermodynamic framework itself. So here's if we're looking at it in the explosive lens. So assuming explosive eruption, it's in a closed volcanic system, and the gases released in the atmosphere would represent the pre-eruptive exsolved volatiles. So whatever that's, so if the reservoir is at, say, 400 megapascals depth, then if it erupts explosively, the normalized SO2 would be equivalent to that at that depth. Whereas if we look at effusive eruptions, these effusive eruptions has the magma moving slower up the conduit, and therefore has more time for the volatiles to exsolve during their magma ascent. And that means these volatiles are in equilibrium with the surface pressure. So they have more time to exsolve as they get to the surface. And these effusive eruptions mean that despite having say a reservoir at 400 megapascals, the normalized SO2 would be higher than that of an explosive eruption. Here we look at the satellite detectability for basaltic eruptions. So we look at basaltic eruptions between 2005 and 2020, and among 61 arc basalts, there's only 7 of them that has satellite detected deformation as compared to ocean island basalts. And that's because arc basalt has more water content in general than ocean island basalts. And it having more water content means that it's more compressible and therefore has less deformation. Yep. However, at the same time, we see that despite arc basalt having more water content than ocean island basalt, we see that less than half of the arc basalts show sulfur dioxide gas that's being detected by satellites, whereas for ocean island basalts, like all of these eruptions show sulfur dioxide gases. That's likely due to the difference between the eruption styles. So arc basalt tends to erupt more explosively as compared to ocean island basalts, which tend to erupt more effusively. So now that's the sense of the conceptual model. So now we add another parameter into it, which is the pre-eruptive gas accumulation or loss. So before an eruption, volatiles could accumulate at the roof of a reservoir, and due to the additional amounts of gas in the reservoir itself, it means that it's more compressible. As compared to pre-eruptive degassing, that means that volatiles that has been exsolved in the reservoir, and although there's no eruptions, these volatiles continue to exsolve and they can escape out of the volcanic system. So in general, volcanic systems that undergo or underwent pre-eruptive gas accumulation, they are more compressible and they could accommodate deformation. So that means there's less deformation that could be detected as compared to degassed magma, where there's better detection of ground deformation. And to calculate these, I use this equation, and I use the proportion K to represent gas accumulation or gas loss. So here's some sensitivity tests again. So here's when we're looking at rhyolite, and these red lines represent gas accumulation. So if K equals to 1, which is gas accumulation itself, we see more sulfur dioxide gas and less deformation, as opposed to pre-eruptive degassing, where we see that there's less SO2 that's being released, and at the same time it has more volume changes compared to closed system degassing. So here are the results. So first of all, we compiled a global observations of volcano deformation and degassing, SO2 degassing. And while I mentioned like global observations, really there's just like 19 eruptions over here. And that's mainly because I need to normalize these two observations with erupted volume, and to have all 3 parameters available for eruptions. So it's very, very difficult. And so really I'm limited to what data that are available online. So here we could separate these magma into two different types. So one being silica rich, that's more than 50%. So that's like andesite, dacite, rhyolite. And then the other group would be silica poor, that's basalt or trachybasalt. So here we could see that there's a widespread of normalized volume change and normalized SO2. Where we're looking at silica poor magma as compared to if it's silica rich, then the normalized volume change itself, it's still fairly widespread between 0 to 0.6, but it's less spread out as compared to silica poor eruptions. Whereas when we're looking at normalized SO2 itself, initially we were expecting these silica rich systems to have higher normalized SO2, considering they tend to be more explosive. But what we've seen over here is that they have fairly low normalized SO2, and that sort of picked up interest. So we further explored this bit of it. So we look at different depth of these eruptions, and here we see that in general, silica poor eruptions has a shallower reservoir depth as compared to these more evolved silicic rich systems. They have like a deeper reservoir depth. And to further explore over there, we compare these observations to thermodynamic models. So it looks complicated, so I'll show you step by step. So on the left panel over here is SO2 versus eruptive volume. And these diagonal lines represent the estimations from the thermodynamic model at different depth. So so for a basalt at 8 kilometers, and if it erupts like this amount of volume, this is the amount of SO2 gas we are expecting. So what we could see over here is that these eruptions generally lie very close to the 0 kilometers diagonal line over here. And that sort of suggests that these eruptions underwent co-eruptive degassing. That means they are effusive, and it's consistent because these are mafic / basaltic eruptions by itself. We look at the normalized volume change, and here we see that it doesn't really lie on between the lines of arc basalt or ocean island basalt. But here we could see that these silica poor eruptions tend to underwent a certain extent of pre-eruptive degassing. And now we look into silica poor systems. So here we've got another complicated one. So I'll show you step by step. So these diagonal lines, these dotted ones, is the thermodynamic models that's predicting the SO2 based on melt inclusion data. And then these full lines are based on primitive melt itself. So we could see that most of these eruptions lie above the 0 kilometers melt inclusion data. And this sort of suggests that these eruptions are more gas-rich as compared to the model prediction itself. So it means that it had underwent a certain extent of pre-eruptive gas accumulation. But if we look into the normalized volume change data, it doesn't really show that. So if we look at melt inclusion data over here, most of these eruptions are just it's not even showing like properly in this bit of it. And then if we look at the pre-eruptive gas accumulation, which is the yellow domain, or the purple domain, that is the pre-eruptive degassing, it shows that there's a fairly good spread over here, but there's only 3 eruptions that's showing pre-eruptive gas accumulation as compared to more over here based on panel A here. So that piqued my interest. So I looked into what if we compare that to a primitive melt, and it shows that actually many of these eruptions, compared to primitive melt itself, many of these eruptions underwent a certain extent of pre-eruptive degassing. It's either that, or it's possible that a melt inclusion data itself is showing some sort of uncertainty. So guess I've got the next slide itself to sort of help to summarize what I've explained in that previous slide. So yeah, silica pore system, which is the top 3 panels over there. The observations of deformation, it shows signs of pre-eruptive degassing, and SO2 emissions are dominated by co-eruptive degassing. As compared to the silica-rich systems, which are the 3 panels at the bottom, yeah, pre-eruptive gas accumulation would result in high atmospheric SO2 yield and muted ground deformation due to the higher volume of gas in the reservoir. But really what we saw just now, if we were to compare both the normalized SO2 and normalized volume change observations, I think pre-eruptive gas accumulation is still happening, but at the same time, pre-eruptive degassing could occur at different parts of the reservoir, and silica-rich systems itself are more evolved, and therefore has a more complex network. So I think pre-eruptive degassing itself could be occurring at different bits of the reservoir, and at the same time, it is possible that the exsolved volatiles could accumulate at different bits of the reservoir, at shallow bits of the reservoir, but may not be captured by the melt inclusions. So it's possible that the SO2 emissions itself could be underestimated. So that's on the conceptual model itself, and moving on to the next bit of my project, that is to look into magma with different layers. So here I've got a 2-layered magma model. So you could sort of imagine that the upper layer is either a degassed magma or a gas-rich magma, and then the bottom layer is just a normal close degassing system magma. So here we've got a upper layer that's that has a proportion of 0.7 and the bottom at 0.3. And here are the different dots representing the bulk gas, or the bulk normalized SO2, or bulk compressibility. So as we remove a proportion of the magma from the top, because as we're erupting, we're removing the upper bits of the magma itself. So as we're removing the upper bits of the magma, the total exhaust gas of the system itself would increase, and that leads to the bulk increase in the normalized SO2. And because of the bulk increase of the gas itself in the system, it means that the magma compressibility is increasing, and therefore it's showing less volume change. And as we deplete the system itself, as we continue to erupt the underlying magma, and because we're just erupting the same magma itself, so that means there's no change in general with these observations. And here I just include what happens if it's a gas-rich cap, and that's just basically the opposite of what I've explained for the degassed magma. So I did a case study on Mount St. Helens, and so these blue dots or blue lines itself are the observation, and using the 2-layered model itself, I simulated what is the sulfur dioxide gas and also the volume change itself, and it sort of shows a fairly good fit, but at the same time, because of the complexity of these data itself, it doesn't really fit well, and yeah, there should be uncertainty lines over here too. And then I did a case study. This is on Column-Collier, and this is an example if it is a gas-rich magma. So we've got data over here, but you could see that based on these dots, it is very, very scattered. And in fact, we've got only one dot over here on the normalized volume change. And that is because we've only got 1 point of volume erupted data. And that means we can't really create a time series of the normalized volume change during the explosive phase. And so what we did over here is we calculate for the normalized volume change based on the volume change and volume erupted data. And this orange dot itself is if we are looking at the explosive phase. And it shows that it has less normalized volume change as opposed to the effusive phase. So that sort of suggests that it has higher magma compressibility, which is shown over here, as compared to during the effusive phase itself. And these lines itself in general, it's just showing what are the model predictions based on different K values. So if it's gas accumulation, or if it underwent certain extent of pre-eruptive degassing. And yeah, so just to summarize, the framework developed during my PhD shows that monitoring the evolution of magma properties could help us to understand and forecast the behavior of volcanic systems. And the key thing over here is that the change in gas content in the magma itself affects both sulfur dioxide emissions and ground deformation. But to really implement this model itself, it's really, really dependent on data availability. So during explosive phase, there's very limited data because I don't think people want to risk themselves to go into like these explosive eruptions. Maybe some does, but at the same time, yeah, there's limited amount of erupted volume. And so we really need to push satellites that are calculating erupted volume. So like say more of 10x kind of satellites. I know that Harmony should be launching this or next year, but hopefully with the availability of Harmony, we could sort of push forward towards this direction. So again, implementing these kind of strategies is critical, but we do need these data. And I shall just end it over there. And if you've got any questions, then just feel free to ask me.
Yeah, thank you very much, Stanley, for a very interesting talk. Just as Stanley just said, yeah, if you've got any questions, put them in the Q&A and we'll answer them. But while we're letting people think a bit more about it, so at the moment, your framework is based on these models. Do you want to talk a bit about some of the limitations that would be important to consider when using them as well?
Yeah, so this framework itself is based on thermodynamic models. And over the past few years, there has been a lot of different softwares or thermodynamic models that are online. Many of them are more friendly as compared to like previous, like the olden days. But so that means we need to know what thermodynamic models to use. And whilst using those thermodynamic models, we need to understand what is their the background of it. So say, for example, what is their sulfide capacity law or their sulfur solubility laws itself. So we do need to have an understanding of the chemistry behind the models. Sorry, yeah, the solubility models behind the thermodynamic models. Yeah, yeah.
That makes sense. No, don't know much about them, but it's interesting to hear those things. I've got a slightly different question, but because you brought up in the end again, the data availability is a big thing here. So most of the work you've been doing is looking using satellite data, but would it be possible to incorporate other data sets, so ground-based observations and stuff into this to help with some of the interpretations? Or
Yep. So I think many of these eruptions itself are, I know in the beginning I mentioned satellite observations itself, but because there's just so limited, we're very limited with these data itself. So I think halfway through, I sort of include basically like GPS data or like just field-based erupted volume data to really to add more into the compilation itself. But I would agree that having more of these data will be helpful. And then if there's a repository somewhere that has everything, they'll be perfect. I mean, that's the ideal world.
yes. You've stunned the audience into silence. Oh, we got a question. That's good. So we got a question here from Graham Ryan, who's asking, can you go over the difference in magnitude of deformation between the volatile rich and the volatile poor systems?
Sorry, could you repeat that again?
I think you can check it. You can see it yourself in the Q&A. Otherwise, I can say it again if you want.
I've got chat previews. Oh, there it is. All right, I see it now. Can you go over the differences in magnitude of deformation between volatile? Oh, yep. I'll just, sorry for like this jump in slides, but yep. So here on the right panel is the normalized displacement itself. And here, obviously we could see that everything just sort of narrowed down at the last few kilometers towards the surface. Right, yep. And let's just say we've got a chamber at 5 kilometers depth. We could see that the increase, if the system underwent gas accumulation itself, it shows less normalized displacement as opposed to system that has underwent degassing. It shows more displacement, or deformation itself is more apparent. The magnitude itself between volatile rich and volatile poor systems. So I guess really it depends on what K value we are putting into the model. So if we put like, say, I don't know, like K negative 0.5 and compare that to like K positive 0.5, then it shows this amount of magnitude. But it really depends on the proportions of pre-eruptive gas accumulation or degassing. I hope that answers the question.
I think so. We've got another one here saying, thanks for the great talk, Stanley. Is there any way to estimate pre-eruption gas fraction in the magma chamber?
So that was the tricky bit I encountered during my PhD. So we could use you could backtrack the calculations from deformation and SO2 gas itself to try to calculate the compressibility and the density. But I think to calculate backwards to the gas fraction itself, we need to understand and know the different solubility laws. And that in itself is another can of worms. It is possible, but I would say I could not manage that within the time frame of my PhD. But it is possible, I think.
Another PhD project, maybe. We've got one more question here, which is awesome talk. Is magma composition, which can be related to deformation, observed at volcanoes in thermodynamic conditions. So looking at dissolvation or exosolvation.
So I'm trying to paraphrase that. Is magma composition, which can be related to deformation, observed at volcanoes or thermal conditions? Sorry, I don't think I get your question. Could you rephrase that, please? Sorry. But I think yeah, I'm not sure if I'm answering this correctly, but I'll still give it a go. So magma composition itself does play a role in terms of the deformation that we're observing. Sorry, the observations that we're observing at volcanoes. The thermodynamic conditions itself does play a role. So it really depends on, as you've mentioned, if it's dissolution, exsolution. But at the same time, we need to consider like if there's like crystallizations or other processes as well, like second boiling. So I would say it's an interplay of a lot of things. So magma composition does play a role. The volatile content itself does play a role too. What is the condition of this system also plays a role. And because each volcanoes are unique, and we can't just we do not have a one-size-fits-all model over here. So but hopefully with my results over here could sort of show you the different end members of what we're expecting.
I think that answers the question kind of. As it's a very complex system, which it's quite. Oh, I think we have a clarification.
Oh, all right. Sorry, I just saw it.
No worries, it just came.
Crystallization. Yeah. So it could occur too, as mentioned with the effusive eruptions. So volatiles are being exsolved during magma ascent of effusive eruptions. So as volatiles exsolve, that could change the composition itself, and as volatiles exsolve, I'm sure that crystallization itself is also changing. And so that means, yes, the composition at the surface and at the source itself is definitely different. But if we are looking at an explosive eruption, then because everything is just happening instantaneously, so we could assume that the magma at the source itself or at the reservoir itself, we could take that snapshot and to calculate the deformation and degassing itself. In terms of effusive eruptions, that would be more complicated, as you've mentioned as well, crystallization during ascent. A lot of things are happening in the vent itself. So it is more it is more complicated than my project could answer.
I think that clarifies it definitely. But yeah. I think that's a good point to wrap things up as well. So thank you again, Stanley, for a great talk and sharing all your amazing work as well.
Thank you for
no worries. I also wanted to say that we have our next webinar, which is currently scheduled for the 4th of December. And it will be given by Rita Kunides from the University of Oxford. And we will aim to get that information out as soon as possible. So thank you again for everyone who came, and we'll see you at the next webinar.